Picture 3 Claude Code sessions running simultaneously. The database agent finishes creating a payment schema and broadcasts the contract. The back-end agent immediately builds API endpoints using that schema. The front-end agent sees the API contract and begins implementing the billing interface. All three work in parallel, messaging in real time, coordinating autonomously. This is Agent Teams. In Part 1, you learned the difference between isolation and collaboration. In Part 2, you mastered subagents for efficient delegation. Now, in Part 3, you'll learn how to orchestrate true AI collaboration, where multiple Claude instances coordinate directly to tackle complex implementation work. We'll cover the coordination problem, setup and configuration, the architecture of leads and teammates, communication patterns, contract-first spawning, optimal team sizing, quality gates, and a complete payment integration build with 3 agents. We'll also cover how to avoid file conflicts, cost-benefit analysis, and troubleshooting. By the end, you'll know when to use agent teams, how to orchestrate them effectively, and how to get production value from parallel AI collaboration. Subagents are powerful for isolated work, but they break down when tasks need coordination. When the database schema affects back-end endpoints and back-end affects front-end interfaces, you can't work in isolation because each layer depends on the others. This is the coordination problem. Let's make it concrete with a payment integration feature. You need a database schema for transactions, back-end API endpoints for purchasing tokens, and a front-end billing page. These 3 layers are interdependent. Back-end queries must match the database schema, and front-end calls must match back-end endpoints. With subagents, coordination flows through your main conversation sequentially. Subagent 1 builds the schema and returns it to main. Main processes and delegates to subagent 2 for backend. Backend completes and returns API contracts to main. Main delegates to subagent 3 for frontend. This works, but the backend can't start until database is done, and frontend can't start until backend is done. Agent teams solve this with peer-to-peer coordination. The database agent completes the schema and broadcasts it directly to both back-end and front-end agents. They receive the contract simultaneously and start working in parallel. The back-end agent defines an endpoint and messages the front-end agent with the route and payload. The front-end updates immediately without waiting for main to relay information. The key difference is autonomy. Subagents wait for your main conversation to orchestrate every step. Agent teammates communicate and coordinate independently, making decisions and updating each other when contracts change. This autonomy enables true parallelism even when work is interdependent. This is when you need agent teams, when coordination between workers adds value and real-time communication prevents rework. Agent Teams is experimental as of March 2026, but setup is straightforward. Enable it with an environment variable in your shell profile or in your Claude Code settings file. Add Claude Code experimental agent teams equals 1. Then restart your terminal. The alternative is split pane mode with tmux or iterm2, where each teammate gets its own pane and you see all outputs simultaneously in a grid. This is the premium experience if your environment supports it. For tmux, install it and configure Claude Code with teammate mode set to tmux. For iturn2, install the i2CLI tool and set teammate mode to auto. Claude Code detects your environment and uses split panes automatically. Your first team spawn is simple. Just ask Claude to create an agent team for a task. Claude analyzes the work, proposes a structure, and asks for approval. You can also specify explicit control by requesting specific teammates and roles. Once running, you'll see the lead in your main session and teammates in separate sessions or panes. The lead coordinates, teammates work. A shared task list shows all work items, and the mailbox enables inter-agent messaging. Agent Teams architecture has 4 core components: the team lead, teammates, the shared task list, and the mailbox messaging system. The team lead is your main Claude Code session that handles coordination, not implementation. It creates the team, spawns teammates with clear instructions, monitors progress, and shuts down when work completes. The lead delegates work to teammates and focuses on orchestration, like a project manager. Teammates are separate Claude Code instances running independently with their own context windows and tool access. Crucially, they don't inherit your main conversation history. When you spawn a teammate, you provide a specific prompt that becomes its starting point. The teammate then works autonomously, claiming tasks, completing work, and messaging other agents without constant supervision. The shared task list distributes work. The lead creates tasks with dependencies, owners, and status. Teammates scan the list, claim available tasks matching their role, work on them, and mark them complete. When a task with dependencies finishes, dependent tasks automatically unblock, creating a dynamic workflow where teammates self-organize rather than waiting for explicit assignment. The mailbox enables inter-agent communication. Any agent can message any other agent or broadcast to all. Messages are delivered automatically, and agents get notifications when messages arrive. This enables real-time coordination. The backend finishes an endpoint and messages the front end with route details, or the database broadcasts that migration is complete. Together, these 4 components enable autonomous agents to coordinate through structured communication and execute true parallel collaboration. Communication is what makes agent teams powerful. Unlike subagents that only talk to the main agent, teammates message each other directly. There are 4 primary patterns: direct messaging, broadcasting, automatic notifications, and task-based coordination. Direct messaging is point-to-point communication. The back-end agent finishes an API endpoint and messages the front-end agent directly with the change. The front-end receives it, updates its implementation, and continues working with no lead involvement and no waiting for relay. Broadcasting sends a message to all teammates simultaneously. The database agent completes a schema migration and broadcasts that the transactions and tokens tables are ready. Every agent receives the notification. Backend starts writing queries. Frontend knows the data structure, and test agents can begin integration tests. One message, everyone informed. Automatic notifications keep agents synchronized. When a teammate completes a task, the lead gets notified. When messages arrive or dependencies unblock, agents learn immediately without polling. This means agents don't waste time checking status. They work until relevant events trigger attention. Task-based coordination uses the shared task list as communication. The lead creates tasks with dependencies. Teammates claim tasks matching their expertise. And when one agent completes a task that another depends on, the dependent task automatically unblocks. The dependency graph becomes a coordination protocol. These patterns combine for sophisticated collaboration. A database agent broadcasts a schema contract. Backend and frontend receive it and start parallel work. Backend messages frontend with endpoint details, and frontend marks its task complete, which unblocks the test agent. This is the advantage. Subagents coordinate through you, but agent teammates coordinate through each other. Contract-first spawning prevents massive rework. The principle is simple. Spawn upstream agents first to define contracts. Then spawn downstream agents with those contracts as context. This eliminates incompatible assumptions. Here's the problem. You spawn 3 agents simultaneously for a payment feature. Database, backend, and frontend all start in parallel. The database decides on a schema. Backend builds endpoints based on assumptions about the schema. And frontend implements calls based on assumptions about the backend. When they integrate, nothing matches. Backend queries columns that don't exist, and frontend calls endpoints with wrong payloads. Parallel execution became parallel waste. Contract-first spawning solves this. Spawn the database agent first, alone, and have it define the schema contract, including table structures and relationships. The agent produces a complete specification and returns it to the lead. Now spawn backend and frontend together with crucial context. Their spawn prompts include the database contract. Both agents start knowing exactly what tables exist, what columns are available, and what relationships exist. Backend builds endpoints querying the real schema. Frontend makes assumptions consistent with what backend actually has. When they integrate, everything matches because they started from the same foundation. This extends beyond database to backend. Any dependency benefits from contract-first spawning. Backend defines API contracts before frontend implements. Design system defines component interfaces before feature agents build pages. Spawn upstream, get contracts, then spawn downstream with context. The cost is slightly slower start time, but the benefit is massively reduced rework. Time saved by not rebuilding far exceeds time spent on sequential contract definition. How many teammates should you spawn? The sweet spot is 2 to 4 teammates for most tasks. Below 2, you're not leveraging parallelism effectively. Above 4, coordination overhead cancels the benefits. 2 teammates works for features with clear separation, database plus backend, or backend plus frontend. 3 teammates is the most common pattern, database, backend, frontend covering the full stack. 4 teammates adds testing, or a second frontend agent for complex UI work. Cost scales with team size because you're running multiple Claude instances simultaneously. 1 teammate is about twice baseline cost. 2 teammates is 3 times. 3 teammates is 4 times. 4 teammates is 5 to 6 times baseline. These are approximations. Actual cost depends on task complexity and agent activity. But the pattern holds. Each additional teammate roughly adds 1 baseline worth of cost because they all run in parallel. Use this framework to decide team size. For simple features touching 1 or 2 layers, use a subagent. No team needed. For features with clear layer separation like backend and frontend, use 2 teammates. For full-stack features with database, backend, and frontend, use 3 teammates. For complex features with extensive UI work or comprehensive testing, use 4 teammates. The key question is interdependence. If layers coordinate but work independently most of the time, agent teams add value. If layers need constant back and forth, the coordination overhead might exceed the benefit. Teammates work autonomously, which means they can make mistakes without immediate oversight. One agent writes code that breaks tests. Another modifies files it shouldn't touch. A third makes expensive API calls unnecessarily. Quality gates prevent these mistakes. Claude Code hooks provide quality gates at 3 points: before tool use, after tool use, and before commands execute. Pre-tool hooks validate before an action happens, checking if tests pass before allowing a write, or verifying file permissions before edits. Post-tool hooks validate after actions, running linters after code changes, or checking the test status after modifications. Command hooks intercept specific commands, like git commit, to enforce policies. Here's how it works in practice. A teammate attempts to write code to a file. The pre-tool hook intercepts and runs the test suite. If tests pass, the hook allows the write and the code is saved. If tests fail, the hook blocks the operation and shows the agent which test failed. The agent sees the error, fixes the code, and tries again. The validation runs automatically. No manual checking required. Configure hooks in your Claude Code settings file. Define the hook type, specify which tool it applies to, write the validation command, and set the exit criteria. If the command returns a non-zero exit code, the hook blocks the action. You can add hooks for any tool, write, edit, bash, git commands, and chain multiple validations together. Common patterns include test validation before writes, linting after edits, permission checks before dangerous operations, and git hooks that enforce commit standards. Let's walk through a complete payment integration build with 3 agents. Phase 1 is contract definition. The lead spawns the database agent first, with a clear task. Create the schema for billing and token purchases, including transactions table, tokens table, and user balance tracking. The database agent works independently, designs the schema, creates the migration files, and produces a complete contract specification listing all tables, columns, relationships, and queries available. The agent broadcasts this contract to the lead, and the lead prepares to spawn the next agents with this context. Phase 2 is parallel implementation. The lead spawns backend and frontend agents simultaneously, both with the database contract in their spawn prompts. They know exactly what tables exist and what queries are available before they start. Backend builds API endpoints using the real schema, post billing/tokens for purchases, get billing/balance for checking tokens, get billing/history for transaction lists. As it creates each endpoint, it messages the front-end agent with route details and payload expectations. Front-end builds the billing interface with placeholder data first, then receives back-end messages with real endpoints. It updates fetch calls with the actual routes, adjusts payload structures to match back-end expectations, and implements error handling. Both agents work simultaneously, messaging back and forth to coordinate changes. Back-end finishes endpoint implementation and marks its task complete. Front-end completes UI implementation shortly after. Both worked in parallel for 7 minutes instead of 13 minutes sequential. Phase 3 is integration and testing. The lead spawns a test agent to validate the complete payment flow. Database schema is used. Backend endpoints are called. Front-end UI interacts with the API. The test agent runs integration tests across all layers, verifies end-to-end workflows, and catches any mismatches that slip through. All agents worked autonomously, coordinated through messages, and completed the payment integration in 12 minutes total with real-time collaboration, ensuring everything fits together. File conflicts are the biggest practical problem with agent teams. When 2 teammates edit the same file simultaneously, one overwrites the other's changes. Git doesn't magically merge concurrent edits. The last agent to save wins, and the previous work gets lost. The problem scenario is straightforward. Backend agent implements authentication functions in utilsauth.js, while frontend agent simultaneously adds validation helpers to the same file. Backend finishes and saves. Frontend finishes 30 seconds later and saves. Backend's auth functions are gone, overwritten. Both agents think they succeeded, but half the work vanished. The solution is clear ownership boundaries. Structure work so each teammate owns completely different files. Backend works exclusively in API routes. Frontend exclusively in components. Database exclusively in schema files. No overlap, no conflicts. This requires planning team spawning around module boundaries, not just conceptual responsibilities. File-based module separation is most reliable. For a payment feature, backend owns everything in API billing, frontend owns components billing, database owns database migrations, test agent owns tests integration. Each has complete ownership of its directory tree without risk of collision. Component-level separation works for larger systems. Authentication agent owns all auth-related modules across the stack. Payments agent owns all payment modules. User management owns all user modules. Each can touch multiple layers as long as there's no overlap with other agents' domains. The exception is configuration files like package.json or environment files. Designate one agent as owner, or have agents communicate before changes. Backend messages "I'm adding dependency to package.json," then makes the change. In practice, if you structure tasks well, Conflicts are rare. Most features decompose cleanly into non-overlapping file sets. The key is intentional task planning. Ask if two agents could edit the same file, and if yes, restructure assignments to eliminate overlap. Let's talk about real costs. A 3-agent team runs at approximately 4 times baseline cost. Your normal Claude Code session might use 50,000 tokens, costing 50 cents. That same work with 3 teammates uses 200,000 tokens, costing $2. The cost multiplies because all agents run in parallel. Time investment adds cost too. Setting up the team, spawning agents with good context, and monitoring coordination takes 15 to 30 minutes. For a 15-minute task, that overhead is expensive. For a 3-hour task, it's negligible. What do you get for that cost? Speed gains of 20 to 40% on coordinated work. A full-stack feature that takes 18 minutes with subagents takes 12 minutes with agent teams. 6 minutes saved. A 3-hour refactor might save an hour through parallel work. Coordination benefits prevent rework. When back-end and front-end coordinate in real time, you avoid the 2-hour debugging session, finding why the API payload doesn't match expectations. When database broadcasts schema changes, you don't spend an hour updating back-end queries to match. Quality improvements come from parallel review. One agent writes code while another reviews architecture decisions. Front-end questions back-end design choices before implementation is complete. Mistakes are caught early when they're cheap to fix. Use this framework to decide if agent teams are worth the cost. Worth it for cross-layer features where database, backend, and front-end all change together. Worth it for complex refactoring with multiple interdependent modules. Worth it for parallel implementation where different agents can work simultaneously on related code. Not worth it for simple features touching one file. Not worth it for exploratory work where you're still figuring out requirements. Not worth it for quick fixes that take 15 minutes. The break-even point is roughly 1 hour of work. Below that, the setup overhead and coordination cost exceed the time savings. Above that, the benefits compound. Common technical issues and how to fix them. First, teammates not appearing. You spawn agents but don't see them. Press Shift+down to cycle through teammates in in-process mode. If using tmux, verify you're in a tmux session with tmux ls. Check that experimental flag is enabled in settings. Second, communication failures. Messages aren't being delivered between agents. Verify mailbox is enabled. It's automatic, but check Claude Code version is 2.17 or higher. Test with Show Task List to confirm agents can communicate with shared state. If messages still fail, restart the team with clean shutdown and respawn. Process issues arise from unclear structure. Third problem, stale tasks that never complete. Agents claim tasks, but make no progress. This usually means task dependencies aren't clear, or the task description is too vague. Review the task list with Show Task List, verify dependencies are correct, and rewrite task descriptions to be more specific about what needs to be done. Fourth, coordination chaos where agents work at cross purposes. One agent undoes another's work, or agents duplicate effort. This means roles aren't clearly defined in spawn prompts. Respawn with clearer responsibilities. Database agent only touches schema files. Backend agent only touches API code. Front-end agent only touches UI components. Add file path restrictions in spawn prompts to prevent overlap. Fifth problem, cost overruns where your API bill is higher than expected. This happens when teams are too large. 5 or 6 agents all running in parallel burns tokens fast. Stick to 2 to 4 teammates maximum. It also happens when tasks run longer than expected because agents are exploring rather than executing. Set clear time limits and specific goals in spawn prompts. Best practices, start small with 2 teammates. Add more only when needed. Use clear spawn prompts with specific tasks and file boundaries. Monitor progress with Show Task List periodically. Shut down promptly when work is done. Don't leave teams running idle. You just completed the definitive guide to parallel agents in Claude Code. 3 parts, 35 minutes, complete coverage from decision frameworks to production implementation. You now know when to use agent teams versus subagents, how to configure them, and the patterns that make them effective. This knowledge is production ready. If this delivered value, subscribe to Byrddynasty. We build comprehensive guides for production AI development, deep technical content that makes you better at shipping real systems. Hit subscribe and turn on notifications for future series. If you implement agent teams or subagents, drop a comment, share what worked, what didn't, and what you built. The community learns from real implementations.
You now have the complete picture of agent teams. We covered the coordination problem, setup and configuration, the architecture of leads and teammates, 4 communication patterns, contract first spawning, optimal team sizing, quality gates with hooks, a complete payment integration build, avoiding file conflicts, cost-benefit analysis, and troubleshooting. Agent Teams is your tool for complex, multi-layer implementation where coordination adds value. Use it when teammates need to communicate, time matters more than cost, parallel work is possible, and complexity justifies overhead. 3 to 5 teammates is the sweet spot. Contract first prevents rework. Quality gates ensure standards. You've completed the full series. Part 1 taught the difference between isolation and collaboration. Part 2 gave you subagents mastery. Part 3 delivered agent teams for AI swarm orchestration. You have the complete framework for parallel agents in Claude Code. Thanks for watching. If this helped, hit subscribe and share with your team. Drop a comment if you build something cool. I want to hear about real-world implementations. This is Byrddynasty. Build the future.